To allow the quantitative study on evaporation, we may use empirical equations to estimate the evaporation rate. Among the reliable empirical equations, Meyer's formula and Rohwer's formula are commonly used. There are some similarities between both equations. First, we need to know the saturated vapor pressure at water surface temperature and the actual vapor pressure of overlaying air. Next, we have a function that correlates the wind speed and evaporation rate. The entire equation may then be factored with a coefficient to account for other factors. This form of equation is also known as Dalton-type equation. Let's implement the empirical equations in an example. We are now looking at a large and deep lake. The water temperature is 18 degrees Celsius, while the relative humidity is 45%. The mean wind speed at 10 meters above ground level is 1.33 meters per second. The atmospheric pressure of the site is assumed to be 1 atmosphere. First, we should determine the values for vapor pressure, namely EW and EA. Given the temperature of water surface, we can calculate EW by using this equation. The unit for the obtained value is millimeter of mercury. When T equals to 18 degrees Celsius, EW would be 15.49 mm of mercury. The value of EA, on the other hand, can be calculated simply by multiplying EW with relative humidity. In this example, EA equals to 6.97 mm of mercury. As for the wind speed, only data for 10 meters above ground is available. In this case, we can use the following power law to assume the wind speed at any elevation, provided it is below 500 meters above ground level. In this equation, constant C equals to wind speed at 1 meter above ground level U1. Since the value of U10 is 1.33 meters per second or 4.79 km per hour, we can now solve for U1. In this case, it equals to 3.45 km per hour. Then, we can proceed with the calculation of wind speed at 9 meters and 0.6 meters above ground level. The results are 4.72 km per hour and 3.21 km per hour respectively. Lastly, we know 1 atmosphere of pressure equals to 760 mm of mercury. At this point, we have successfully identified all the inputs for both Meyer's and Rohwer's formula. First, let's look into the Meyer's formula. The value of constant Km is taken as 0.36 for large deep water body. As a result, the evaporation rate is estimated to be 3.97 mm per day. As for the Rohwer's formula, we can simply substitute all available parameters. Using this method, the evaporation rate is estimated to be 4.03 mm per day. Apart from empirical equations, we may use analytical method to estimate the evaporation rate. Water budget equation and energy budget equation are some examples of analytical method. Water budget equation is deemed the simplest method, but its result can be unreliable. You may learn more about it from our previous video. Energy budget equation implements the principle of conservation of energy. By knowing the incoming, outgoing, and stored energy amount, we may then calculate the energy reserve for the evaporation process. When the time period is less than 1 week, energy budget equation gives reliable result. In short time period, energy stored in water body and those dissipated via advection would be negligible. Heat loss to air and evaporation are correlated with Bowen's ratio. This ratio can then be calculated by knowing the atmospheric pressure as well as vapor pressure and temperature for both water surface and overlying air. The remaining energy flow may be measured or evaluated indirectly. Analytical method usually gives better estimation when compared to empirical equations. In return, we need to determine the parameters which are difficult to assess in the first place. Thank you for watching. If you find this video helpful, please share it with your friends. We'll see you guys soon. Goodbye.